was not, you couldn't hear it. But you watched the video from Monday and you could hear me?
Here, I also use like it has the AI do the subtitle.
Uh-huh.
So I kind of compared it, put earbuds in and turned the volume.
All the way up?
It was pretty.
Okay. Why do we think that that is? I mean, it's an iPad, so it has a. Maybe if I wore headphones with a mic, like an earbud with mic. It was hard to hear though. Yeah, bummer. I wonder. There's this thing, you see how that says audio? Maybe I don't want to share the audio. Maybe that's making it have like a, let's see if we can do it without. Maybe it will have no sound at all. What did I hit? Oh, the volume. Okay, we'll give this a shot. How's that sound? Good. To share my screen. Why has that become a thing I can't do? Oh. Thanks. You're paying attention when I did that earlier, huh? Good for you. Thank you. That's right. I need you, y'all. I did the dumbest thing. I swear I am smart, and like obviously I am a little since I got into this point in my life, but I now I should go back and check, and I don't know. On Monday, the first classroom that I taught in, the boards on the podium don't work. So like plugging into to record in Teams, I can't do because I can't share my screen in two places. Right. So I have to actually plug in physically to the podium projector so I can share my screen in Teams. Following what I'm saying? If I do AirPlay in the classroom, I can't also share my screen inside of Teams. Okay, so cord is important. Cord on the podium doesn't work. I put in a work order. I'm like on top of it. Yes, put in a work order. Fix this thing, you know? Yesterday afternoon, I got an email that was like, good news, the cord's working now in Ashby Hall 103. The cord has been working all week. Still works. You know where it doesn't work? Classroom, Ashby Hall 109. And I don't actually know if I put it wrong on the thing, but I honestly have always had trouble with specifically. Like I cannot get them right. I like walk down the stairs every time. I'm like, I should have triple checked. I don't know. Anyway, the work order for the thing, the cord in here that's been working this whole time, been closed. This still works. I'm really grateful that it doesn't now not work. Hopefully though, next week the one in the other room will work too. Good. Okay, so today we finished on Monday. We talked through logical equivalence, building truth tables, negating or an and statements, and what De Morgan's laws are. I think that it went pretty well. Y'all seem to understand what we were doing when we were doing it, right? Okay. So the thing we're going to do today is talk about some common logical equivalences. And before we do that, because these things, and you can see, the bolded T is called a tautology. That is when the final column is all truths. A contradiction is when the final column is all. So that's going to be A tautology is all truths. A contradiction is all falses in the final column. Okay, so common logical equivalences. If we're talking about P and a tautology, that's going to be equivalent to just P. Because if it's P and something that's always true, in order for that to be true, P needs to be true. Okay, let's move down. So P or something that's a contradiction, so something that's always false, this sort of thing is going to only depend on P again. So it's P or an always false statement. So if P is true, then the whole thing will be true. P or P is just P. P or something that is always true is always going to be true. P and something that's always false is always going to be false. P and P. Those ones are kind of, I mean, I think that they are straightforward. Associativity, also pretty straightforward. You can use those parentheses in any order you wish. So you can do P or Q or R. Notice these are like both of those things are the same connector, like they're both or on this one. On the next one, they're both ands. Same thing. You can just switch the order, do Q and R first, and then talk about P. Distribution is a little bit different. Notice the difference in these two things is that the symbol, or there the symbols match, and here they don't. So it doesn't apply. But distribution does. So what you're going to do is this whole thing. You're going to distribute the P or. So you're going to have P or Q and P or R. So you're distributing this like both of those, keeping the like middle. Similarly here, you're going to distribute the P and, so P and Q, or P and R. Again, distributing this to both. Questions so far? We're doing okay. De Morgan's laws. What happens with De Morgan's laws? I have not P or Q. Good. Yes. Not P and not Q. What about not P and Q? It does become an or, and we negate the pieces. So we're looking at not P or not Q. Let's skip absorption for now. We'll talk about negation first. So if I have P or not P, it's going to be true always, right? Because it's either P or it's not P. If P is true, then not P is false. Doesn't matter. The whole thing's true. If P is false, then not P would be true. So the or statement would. So this is just a tautology. This is going to be always true. P and not P, that's the contradiction. Yeah, that one's always going to be. Can't be both P. Okay, so the absorption laws are really strange. They notice that like they look sort of like the distribution because you have the different symbols here, but you're distributing one. This is just, let me talk to you. I normally draw a Venn diagram, but I've decided that maybe that's a terrible way to do this. So let's talk about just P. So we're saying that this whole thing, the truth value of this whole thing depends only on what's going on with P. Okay, so if P is true, if P is true and Q is false, right? Well, this thing is false, but this is true, so it's going to be true, so it matches P. If P is false, right? If P is false, then this thing will be false over here, and this will be false, so this will be false, so it'll match P. If they're both true, great. This is true and true, so that'll be true. Then you have true or true, which will be true, but that'll match the truth value of P. Same thing is happening with this one down here. Let's say that we have true or false. So this is true, and then I'm looking at true and true. Well, that's going to match what P is. If I have, say P is false, this is false, or argument's sake, that's false. I mean, that's true, sorry. That's true, but then you're looking at false and true, which would be false. So that still matches. So the absorption thing, the absorption laws, it takes, which is really nice because it takes something that's pretty complicated and can not complicated at all. It looks like it's some. And do those sort of make sense? So the reason that we can do this is because if two statements are logically equivalent, then you can either do a huge truth table to prove that they are equivalent, that their final columns match, or you can use a string of these things, kind of like you would use algebra to prove like an equation equals a thing. You can make these moves using these things to get from like the left-hand side to the right-hand side. Does that make sense? So you can do either one. We're going to do that now with this example on number 1. We're going to show it with both a truth table and using common logical equivalences so that difference. It's, you know, just it's the same thing. So you want to show that P and not Q or P and P are equivalent so that this thing is a tautology. You could also show that this and this have the same final column, which is how we're going to do it with the truth table. With the common logical equivalences, I'm going to show this is equal to this. Or I can show it's equal to just P. Okay, does that sound good? Okay, so for the truth table side of this, we're going to separate this into pieces. So we have P, Q for our first 2 columns, and then I'm going to have a not Q. I'm going to have a P and not Q. I'm going to have that or P. I'm going to just rewrite the column P to show that they are equivalent. Or do you want me to show that the and P thing is a tautology? Which one do you want me to do? First thing. Okay. Thing I already wrote down. That's good. Okay, so we have true, true, false, false for our P column. True, false for our Q column. Not Q is false, true, true. P and not Q. And statement, I need them to both be true. So I have false, true, false, false. Sorry. Okay, so now we're looking at an or statement with the first column, so I'm going to have true, true, false, false. Hey, looky there. Okay, so what we're going to do right now is to do the same thing with these common logical equivalents. They're the kind of the beauty with this, the same with solving an equation or doing an identity proof or something like that, is that there are a lot of different ways to go about it. So we can chase a rabbit one of you wants me to chase. We can do what I did. What do y'all want to do? Somebody want to try? Do we even understand what I mean yet? Okay, Brian the chemist is going to go for it. Sorry, you. Wait, hold on. Sorry. We're doing the, no. We're doing the first one. My brain did not follow all of that because we're doing this. This what you're saying? Okay. The PVP and not QV. Okay. Okay. Hmm. Mm-hmm. So this is just P. Yeah, so that follows we're looking at P and P. Well, that's just P. What do you think? I think that that was a typo I made. That's not always true. That's not equivalent to a totality. I even wrote that down here. I was in truth tables or logical equivalent. Just let's do some real-time editing. That doesn't make sense. And this should just be equivalent to P. And we did that. Sometimes when you get your eyes wrong, you go back and try to fix them on a smiley face, and then they get really, really creepy. Have you ever done that? Like, oh, no, no. I should have just erased and started over. Okay. So I don't know what, I'm not sure what's going on there, but we have fixed it now, and it does make mathematical sense now, and also logical sense. So I feel good about it. Do you? Okay. Oh, we should do number two. Okay, so we want to show, we're going to do this one just with the equivalences. We're not going to do this with the truth table because I don't like writing truth tables. Really, because we don't need help with that. We can do that. All right, to show that not P or not P and Q is equivalent to not P and not. You don't have to, you can. It's a choice. You can do whichever one you want. First thing that I did was switch the distribution property. The P or not P is always going to be true. This is a topology and a thing, so that only depends on negation on the outside. You can
this is like less writing than doing a truth table, but perhaps more thinking. Yeah, yeah, which you guys should be good at, right? In theory. In theory. Okay, so that is how you're going to do that. Now, I think that was 5 on your. I guess you could do that on 8. Okay, keep going. Y'all ready? Yes? Okay. What is it to do with this? Oh, okay. See, this is this is the first time we're doing all of this, but y'all are gonna have to help me catch stuff like that. That doesn't, you know, I'm doing this by myself, looking at it in code and not in like yeah, and always see things like random parentheses. Thank you. I will try to fix that today if I remember for the next time I do this. Okay, so conditional statements, we talked about them a little bit a while back. This is our if-then statements that we do. We did this already, right? This was one of our connectives we talked about. Yes? We had not, and, or, and then if-then. So we're going to talk more than we might want to about conditional statements. So we have these statements P and Q. This is an implication. If P, then Q. This is denoted by P arrow Q. Q is true whenever P is true. So this is the weird thing about this, and we talked a little bit about this before, that the only time where if P then Q is false is when P is true, but Q is false. Why did we decide that that's true? Right, yeah. The implication is that if the first thing happens, the second thing will happen, right? So the time when that's not true is when the first thing does happen and the second thing doesn't. Right? Did you notice how what both of us said, neither of those things was an if-then statement? We both made and statements, right? I said but, I think, but I mean and, right? And so that's the kind of thing, and we talked a little bit about this too. The interviewer says if you show up for work Monday morning, you're going to get the job. So what has to happen for this statement to be a lie? That you do show up and you don't get the job, right? Notice again, that was an and statement. Yes? So that's the thing. If you don't show up, then the implication is irrelevant. Right? The conditional statement doesn't matter. And we're going to go with innocent until proven guilty, kind of a thing. Okay, so this truth table, sorry, what happens if this is a lie? You show up and you not get the job. And no, we're going to assume that the person wasn't lying. So your truth table is true implies true. So you show up and you get the job. You show up and you don't get the job. That's bad news. You don't show up. Well, we're going to assume they were telling us the truth. So this is when you're lying. Whoa. Lying. The end. So the like thing that is perhaps most bothersome about this is that when the hypothesis is false, when that P part is false, the statement as a whole is true. And like that's, could be bothersome. It is weird, but it is how it works. So we want to talk about when these statements are false. So what does it take for a statement to be false? An implication to be false? P part happens and the Q part does not happen, right? Or true implies false. Yes? Okay. If you get 100% on the final, then you get an A in the class. So when would this be false? Yes. Okay. If Juan has a smartphone, then 2 plus 3 equals 5. What has to happen for this to be false? It's false when one has a smartphone. And 2 plus 3 does not equal 5. But 2 plus 3 does equal 5 always. This is never false. Think about this, that it doesn't matter if one does or doesn't have a smartphone. This implication is always true, because the second part is true. If you look back at the truth table, in which of those columns is the second part true? Or rows. Which of those rows is the second part true? The Q part true. In 1 and 3. And what's the final column in those rows? So this is a statement that would go, it's either one of these options because it's true. So this like implication never going to. Weird, huh? Look at this one. If 2 plus 3 equals 6, then 2 plus 7 equals 10. When is this going to be false? False when what? It's false when 2 plus 3 equals 6. That can't ever happen. 2 plus 3 isn't 6. So this can't ever be false. So it's always true. Yes. Logically, we have to agree with you, yes. But 2 plus 3 doesn't equal 6, so this is never false. Because because that first thing isn't true, right? That if 2 plus 3 equals 6, because we have made a ludicrous statement here, we're in the innocence of proven guilty wrong, right? So we have lost our mind, instead of saying that is faulty, but the logic is not faulty. So this is weird, it's trippy, and this is why we're talking about it, because it's a hard thing to sort of, like, I have to write down all of the things. We were talking about this earlier. Like, it's okay to need to write down stuff and to like follow the, because what happens when we start to do a bunch of steps in our head is that we're going to lose track of stuff and you know. But anyway, because it's ludicrous, it seems like it should always be false, but turns out it's always true. Here are some truth tables we're going to do that involve implications. So I don't know how many. So you guys are going to do number 3. That's on your homework. And so is number 4. So we're not going to do that right now, but we can do 1 and 2. Sound good to you? Okay. So let's do number 1. We're going to write a truth table here. So I have P and Q. Not Q. P or not Q. I am assuming that this is supposed to be like this. P. Then we're going to go with 1 implies 2. How about y'all do it on your own? I'll do it on my own. There are answers. And right. Oh, okay. All right. You ready to do number 2? How many rows should you have? Rows? At least 2. How many rows do you have? How many elements do you have? 8 rows. Why? Thank you. No. 8 rows. Okay. Y'all know it's really sad. I don't know if this is really sad or not. I'm sorry, I shouldn't talk to you while you're trying to think. Never mind. Sorry. I don't, I'm writing a column, so I don't have to think too hard, but you're trying to do trues and falses already. Okay, I'll be quiet. I'm gonna be all right. Need lines. Can't follow what I'm doing. Ah. What happened? Yeah. Lines would be helpful. Emily, where do we differ? It is. Okay, which part? Wait, the first part is true. If the first part was false, it would be true. Yes. Yeah. Yeah. Did you do your 3 rows in this, your 3 columns in this order, or do you have R and P swapped? Do you have true, true, false, false, or do you have true, 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 P? Okay. And they should match. But yeah, on that 5th row, the P to R is true to false, so it's going to be false. You showed up and you did not get the job. Eunice, we are on page 7. Final column. This one? In that same, this guy?
Yeah.
Because this is an and not an implication, I need them to both be true to be true. Yeah, if that was an arrow, you're right, that would be true. We're trying something different with the microphone so that maybe I'll have volume. Why didn't you tell me that that was a problem? I tried to watch a video from my class yesterday to see how mean I was to a student, and was like, oh, I can't hear myself, which is good because how mean I was, but told me. But I tried this one, maybe it'll be better. You let me know. Okay, I tried something different. If I need to, I can wear a thingy. Okay, did we do number 2? Did we get number 2 all together? Okay, so you guys are gonna do 3 and 4 in similar ways on your homework. Right, aren't those both on the homework? Thought I put them on there. You never know what I have actually done. Yes, number 5, that's number 5. 8, that's an 8. I can read really well. I can tell numbers very well. Number 8 on the homework is both and for extra. Your lack of nodding has me concerned. But are y'all seeing the same thing I am? It's both of them, yeah. Number 8, the first part of number 8 to show that, and the second part of number 8 is to show that. Don't skip that. The loaded homework question. It's not. Those are very short. Those truth tables are very small. And yeah. Okay, let's write the negation of this statement. If my car is in the repair shop, then I cannot get to class. So my car, I'm going to put symbols, cars in the repair shop. What letter do we want to use? P is a bad choice. I'm going to use R for repair shop. If my car is in the repair shop, then we're going to go with not C because I cannot get to class. Oops, sorry. Sorry, not C. How would we negate this statement? Well, let's just write it down. R implies not C. How do we do this? RN, not C, so just C. The only time an implication is false is P and not Q. So to negate an if-then statement, the negation of an if-then statement is P and. The negation of the implication is P and not Q. Right? Yes? If it's raining, then the ground is wet. Negate that statement. When is that false? If it's raining, then the ground is wet. Raining and the ground. You got it in words, in symbols, this is what it does. You take this conditional, you put the negation on the outside. When you distribute that negation, it changes, like, what's happening there is that it changes to the first part happens and the second part does not follow. So that, and the second part does not follow here because it's not C. I write that step down. Why is it not R? Yes. Hold on, I can't think in right. Because again, for a statement, for an if-then statement to be false, the first part has to happen. So that's why it's not R. If then. They say, yep. Right. So it's the first part happens and the second part does not happen. So this car is in the repair shop and this child can get. I'm the child. It's me. My car is in the shop. Oh my word. Oh my God. Okay, so some options. The conditional statement is P implies Q. The converse of P implies Q is Q implies P. Just skip down to the inverse. The inverse of a conditional is not P implies not Q. The contrapositive is those ideas together, negated and backwards. So the way the way that I remember the inverse is that inverse sounds like an in, and negation starts with an in. So we're going to negate the pieces, right? So it matches the order, but we're going to negate the piece. Yeah. Converse, backwards. Where's converse all the time? Backwards. And contrapositive is the longest word. So stuff going both negated and not all of them. Are equivalent pairs. Pairs too. Who knows? Let's do some truth tables and figure it out. Okay. Conditional, we can do this truth table. This is going to be true, false, true. The converse. We're going this way. We have true, true, false, true. Not those two. All right, not P, not Q. I'm going to do those. False, false, true, true, false, true, false, true. This is contrapositive. We are going this way with that conditional. So we have true, false, true, true. You have a guess about the pairs now? Mm-hmm. Okay. We have false, false, true, true, false, true, false, true. Ooh, that F looks a whole lot like a T. True, true. Uh-oh. False, true. Hmm. Oh, that's an eraser. Shoot. There. Okay. What do y'all think? Good? So the converse and the inverse are equivalent, and the conditional and the contrapositive are equivalent. It's pretty fun. Okay, what you guys are going to do right now is together, Eunice, can you come and write this up here? I have to pee very badly. I'm going to go. Could you do this? Yeah. Okay. Pencils here. Just write it on there. Okay. Guys, let's do this.
Write a following statement in if-then form and then write the contrapositive, converse, and inverse. So a number is even whenever it is divisible by 2. Okay, so let's do P as is even. Okay, and then Q, I guess it is divisible by 2, right? By 2. Okay. So rewrite as if P then Q. So who wants to say how that would look like?
Number is 10.
Yay! Even and is visible by 2. Okay. Contrapositive. So there would be negation of Q. If it is, yep. by 2, then it is not even. Yay! Okay, converse. Converse would be Q. Okay, wants to do converse. By 2, then number. Perfect. And then the last one is inverse, would not be Q. Not. The first would be, yeah, you're right. Almost done.
You're doing great.
Thank you. My handwriting is not the best, but
It's so fancy. Look at that. Yeah. Wow.
Admittedly better than.
with the number not even, then it's not even spot. Good job, guys. And I don't have space. I hope this is right.
Y'all think it's right?
Well, we did it together, so.
Yeah, see, I'm sure it's perfect. Y'all are all right together. The orders are all backwards. The Q and the P are switched. Because this is hard and this is my fault for giving you this hard example and leaving to go P. It's Q whenever P. So these are all backwards, but let's just let's just write this as a number is divisible by 2 whenever it is even. Then it's all right. Some of these are very tricky. They're like P only if Q is weird because P if Q is different. Like notice these two in particular. This is what I'm talking about. Q if P, P only if Q. These are both a P implies Q. The only if is because of the contrapositive. Because if not Q, then not P, and that's equivalent to the conditional. That's why the P only if Q. The P whenever Q whenever P is, well, if P happens, then Q will follow. That's why it's that Q whenever P. Oh, heavens no. Oh. But like having a knowing sometimes like they're not going to be written explicitly as if then statements and like having to think through like which one is the hypothesis here and which one is the conclusion and having this to like flip back to if you're, feeling lost or whatever. I'm not testing you on that specifically, so I'm gonna write the stuff as if only if then statements. But when you get into like two of you, when you get into other math classes and you're writing proofs and stuff or trying to prove things like knowing, being able to go back and look at this would be helpful. Okay. Good job. Now, We have if and only if statements. That's every definition is an if and only if statement. This is an if and only if statement, so the order doesn't actually matter, right? Because it does mean both number is divisible by 2, or a number is divisible by 2 if and only if it's even. That's an if and only if statement. What that means is that you can start with P implies Q, or you can start with Q implies P. Both are going to be true. It's called a biconditional because it's conditional this way and it's conditional this way. So if the arrows going both ways, you sort of just mash them together and you get this double arrow thing. That's an if and only if. You guys would probably, when you use this in a program or anything, you would use IFF or if and only if. Yep. So these are if and only if statements. They are true when both conditionals are true. When would be the only two times that that happens? Yep, true, true, and false, false. But let's go through it. So conditional, P implies Q. We have true, false, true, false. The other way, we have true, true, false, true. This is in essence columns 1 and 2. That's what the double arrow is. True, false, false. Oh, I messed up. This is true. And then this actually makes sense. What do y'all think? Does that make sense? If you're talking about like P, if and only if Q, and this is the beginning, this, can be true or false as long as this one, if this is true, this isn't false, right? But then going the other way, like you can't have these two. So this arrow is fine, this arrow is fine, this arrow is not fine. This arrow is fine, but this one's not. Both of these are fine. That's why the biconditional works the way that it does. Okay, so often, like I said, we make if then statements. So like if a number is even, then it's divisible by 2. But that's actually a definition. So it should be an if and only if statement. Sometimes though, like the actual use of if then is only one direction. So in Cal 1, you have this like, this is a mathematical example of this not working, or of this in action. So a function has a local, if a function has a local extrema at x equals c, then c is a critical value of the function. This is a true statement, obviously. So let's find the critical values of this function x cubed. What are the critical values? Why? Okay. Is there a local extrema there? Why? Does this contradict the theorem? Why? Right. Yeah. It doesn't say that if and only if a function has local extrema, then it has critical value or whatever, right? This is if you're at a local extrema, then you know it's a critical value. There are more critical values. This is a local extrema implies a critical value, but it doesn't go the other way. Good? Okay, let's keep going. We have, we're now going to talk about arguments. Woohoo! So an argument is a sequence of statements that ends in a conclusion. A valid argument is an argument in which the truth of the conclusion follows the truth statements, which are called premises. So if the premises are all true, then the conclusion should also be true. That's what that means. You good? Okay. Number one, here's an example of an argument. If you are taking this class, then you are a student. You are taking this class, therefore you are a student. So the premises are this guy right here. We're going to call this P1. This is P2. And this is your conclusion. Your premise is if you are taking this class, then you are a student. So let's go with class implies that you're a student. You are taking this class. Think about this like you're therefore bar, you're equal bar and adding or something. Therefore, you are a student. I'm going to move this all where it's lined up. Hold on. Class implies you're a student. This is class. Therefore, those three little dots mean therefore, y'all, student. Is this a valid argument? If you are taking this class and you're a student, you are taking this class, therefore you are a student. Yes, this is valid. Yeah, you are a student. Okay, let's try a different one. Premise one, we have if you are taking this class, then you're a student. You are a student, therefore you are taking this class. Looks a little bit different. This would be like you're taking this class, then you are a student. You are a student, therefore you're taking this class. It's not valid. Why? Yeah, you may not need to take a math. Certainly not this one. Right? Okay. So when determining the validity of an argument, we're going to assume the premises are true, even if they're ludicrous, right? So that's fine, but we're just trying to figure out if the logic is sound. So the argument is valid if the conclusion is always true when the premises are. An argument is not valid if the conclusion is sometimes false. This means when you do a truth table for an argument, your final column should be a tautology. All truth. Yeah? Symbolically, that's a little bit confusing and there's a lot going on, so I'm going to walk you through that. So symbolically, you look at an argument like this. Premise one and premise two and premise three, blah, 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 all of those together with a conjunction, so an and statement. These imply our conclusion. That's the big statement. So premise one and premise two and all the way up to whatever, however many you have. But these imply your conclusion. And so when you do this whole truth table and you get a tautology in your final column, that would be this whole statement, then the argument is valid. There is a different way to do it. And I'm going to walk you through that too. Okay. That first thing that we did, if you're a student taking this class, I'm sorry, if you are taking this class, then you are a student. You are taking this class, therefore you are a student. This is a valid common logic form called known as Conan. You write that as P implies Q and also P, therefore Q. That makes sense, right? If P implies Q and we know P, then duh, we get Q, right? So this is your this is modus ponens. We're gonna do, we have a couple more common logical equivalences or rules of inference we'll talk about in a minute. Okay, so what we're gonna do right now is show that that is valid. So we are gonna show symbolically what this argument looks like is premise one. Remember, we're looking premise one and premise two together imply our conclusion Q. P1, this is P2, this conclusion. So we are looking at our statement here is P implies Q and P implies Q. Okay, so we're going to do our truth table. We have P, we have Q, we have P implies Q. We're going to have P implies Q and P. We're going to take that and we're going to imply our conclusion Q. You get to hear pause with me. Okay, so we can stop. We could really have stopped before this. Like, let's say, I don't want to cross through all of this. The fact that I have this true right here, that true is where all of the premises are true. This is the and with premise 1 and premise 2, right? So this is the only row in which both my premises. I could look at this way too, like I need both to be true. It's only happening in that first row, right? So what I need to know is for my argument to be valid, the truth of the conclusion has to follow the truth of the premises. This is the only place where the premises are true. Is the conclusion also true in that row? Yes. So you're done and it's valid. Why does it not matter about these guys? Yeah, when you're doing an implication at the beginning, you're going to get the truths. So the place where it matters is where all of your premises are true. Is your conclusion also true? That's called a critical row. And there's only one of those here. You can do the whole truth table. No one's telling you to stop, but you can stop. And then talk about the fact that this true follows this true means the thing is true. The argument's valid. Not necessarily true, but valid. We'll do more next time. I'll see you guys next Friday, which is a long time from now. And you're going to turn in homework 1 to me then, and I'm going to load homework 2 in Blackboard before then. I'll be around if you need help. Oh, next Friday. But Eunice, you do need to do the other thing in Blackboard. I put a like mini assignment in Blackboard. It's like a question. What was the question, Sharon? What was the question? Do you like math? You know, you answered it for Ryan. something like that, just to have a record of you being here around. Still happy?
Yes.
Okay. I'll be there Tuesday, 10 to 12:30.